We do not know what filled the void before there was such a thing as before. All we know is that all of a sudden, there was everything, and everything was in an everywhere that was the size of almost nothing. All of everything that ever has been, all that is now, all that there ever will be, came into being in a single instant, occupying a universe smaller than even the tiniest fraction of space. This was the Big Bang. The immense amount of energy spread out rapidly, and, as it occupied more space, began to cool. After only 1/1,000,000th of a second, the universe is still 1,000 times hotter than a supernova, and the entirety of the universe is stuffed inside an area smaller than the Earth's orbit around the Sun, with matter 100 times more dense than in a neutron star. 1 second later, the universe was already nearly 10 light-years across, large enough to encompass our entire solar system and the nearest 7 stars. At this point, protons and neutrons have just formed for the first time, but everything is still too hot for them to form atomic nuclei. Compared to the first second of existence, the next several 100,000 years are relatively uneventful. Everything cools down enough that nuclei can form from protons and neutrons, but electrons are still too energetic to fall into orbitals and create the first neutral atoms. All of the photons created in the Big Bang's burst of light and energy are trapped in this hot plasma and are unable to escape, making the entire universe opaque. Finally, after 370,000 years, electrons combine with atomic nuclei, and the photons are allowed to move freely, at long last letting the light from the Big Bang fill the universe. This last scattering surface forms the cosmic microwave background, what we now see as the diffuse remnant of our universe's creation. This is as far back as we can look toward the beginning of time. The universe continues to expand rapidly. Rather than spreading out evenly in space, however, matter begins to clump together. Why does this happen? Every piece of matter is attracted to every other piece of matter by an invisible force called gravity, which rapidly weakens as the distance between the objects increases. This means that things that are close to each other tend to get closer to each other, and this increases the attraction they feel, so the rate at which they move towards each other also increases. The initial asymmetries in the universe cause matter to draw itself into a filament structure similar to a spiderweb, where strings and clumps of matter outline large voids that are comparatively empty. Along these filaments, there is enough matter in a small enough area that it can collapse into many billions of stars, forming galaxies. The intersections of these filaments have an even higher concentration of matter, allowing them to form clusters of galaxies that number in the hundreds or thousands. Each galaxy contains 100 billion stars, and the universe itself contains over 100 billion galaxies. The scale is nearly incomprehensible. The question still remains as to how these 10 billion trillion stars formed, what they are made of, and how they age and die. Understanding the birth, life, and death of the stars allows one to understand the engine that drives the evolution of the universe. Every star's story begins with a cloud of gas and dust. Despite being dense on an astrophysical scale, the material in these clouds is still sparse and occupies a volume multiple light-years across. Initially, these clouds are relatively stable, as the pressure caused by gas molecules bumping into one another is enough to counteract the gravitational force drawing them together. However, if a region of space achieves a high enough mass, either through random chance or perhaps a passing pressure wave from elsewhere, the gravitational attraction will be enough to overcome the gas pressure. The concentration of mass at the center will grow larger and larger, causing its gravitational pull to grow along with it. The mass in the surrounding area will be increasingly drawn to the center in a cascading collapse. As the gas, which is mostly hydrogen, falls inward, the increasing acceleration makes it move fast. This high speed means the gas has a large amount of kinetic energy. When gas molecules collide as they are moving toward the center of mass, they release some of this energy as heat, so the gas heats up over time. Eventually, after upwards of hundreds of millions of years of falling inward, the cloud has collapsed into a ball surrounded by a rotating disk of excess material. With the temperature and pressure ever increasing, the hydrogen at the center of the ball reaches a critical threshold where there is enough energy for the hydrogen nuclei to combine into helium nuclei. This process, known as nuclear fusion, releases immense amounts of energy, which in turn kickstarts more fusion in a massive chain reaction. At this point, the radiation pressure from the photons released in the fusing core stops any further collapse, and the gas ball can properly be called a star. Within any massive gas cloud, many collapsing pockets can form and lead to the creation of hundreds of stars simultaneously. These stellar nurseries are known as nebulas, and they lead to the creation of star clusters when all of their gas has either been used up or driven away by the stars born within. Moving back to our baby star, things are still not looking quite like how we know our own solar system to be. Rather than being surrounded by a series of planets, the star is surrounded by what is known as a circumstellar disk, which contains all of the leftover material that did not fall into the star. Within this disk, clumps form similarly to how they did in the nebula. Dust particles made of rock, metal, and ice bump into each other and form larger and larger objects, much like a snowball rolling down a hill. Planetesimals, or small rocky and metallic cores that may eventually form planets, are created at varying distances from the star in the so-called protoplanetary disk. The largest of these planetesimals clear their orbit, which means their gravitational pull is strong enough to collect most of the other material orbiting the star at the same distance. This creates the banding effect seen in images taken of protoplanetary disks, with dark spots indicating gaps where a planet is forming. In the outer reaches of the fledgling solar system, where the star is too dim to melt ice into water, the largest rocky planetesimals, usually a few times the mass of Earth, vacuum up the remaining gases and form thick atmospheric shells. These planets accumulate so much gas that it becomes a primary component of their mass, and they become known as gas giants. In our own solar system, Jupiter and Saturn are the most prominent examples. Some gas giants are so massive that they are only slightly smaller than the weakest stars. In the inner solar system, on the other hand, the radiation coming from the star excites gases and makes it more difficult for planets to hold onto large, puffy atmospheres. Instead, rocky planets form, often with a metallic core, ranging from as small as 1% of Earth's mass up to 10 Earth masses, although so-called super-Earths are rare. Mercury, Venus, Earth, and Mars are all examples of rocky planets. Some of the more massive rocky planets still accumulate a small atmosphere, like Earth and Mars did, and these atmospheres can also be enhanced by volcanism on the planets, like in the case of Venus. The excess material in the protoplanetary disk either accretes onto a planet, falls into the star, becomes ejected from the solar system, or forms debris rings similar to our own asteroid belt. While this process does not play out exactly around every star, scientists believe that most stars have at least one planet, and that there are more planets in the galaxy than there are stars. Now that we have a star and a fully formed planetary system, what happens next? Answering this question requires an understanding of the life expectancy of stars. As they shine, stars convert the hydrogen in their cores into helium. Eventually, a star will run out of hydrogen and not be able to continue the same fusion process. More massive stars run out of hydrogen quicker, as the greater pressure causes it to fuse at a faster rate. When there is no longer enough hydrogen in the core, stars will start fusing helium, but this is a much less efficient process, and the supplies do not last nearly as long. During its slow death, a star will fuse heavier and heavier elements in less and less efficient processes, burning through the available fuel quicker each time. The next step depends on how massive the star is. For lower mass stars, usually less than 8 times the mass of the Sun, the star reaches a point where there is not enough pressure to start the next phase of fusion, and the star expels most of its outer shells into interstellar space. The core of the star becomes a white dwarf, an extremely dense object the size of Earth that no longer undergoes fusion, so is left to slowly cool for billions of years. These white dwarfs are surrounded by a planetary nebula, which is a cloud of hot gas that was ejected from the star in its death throes. In more massive stars, the fusion process continues due to the higher pressure in the core. Eventually, iron, an atom with 26 protons, will start to be produced in the core. There are no iron-fueled fusion processes that would lead to a positive output of energy, so fusion in the core stops. With no more radiation pressure supporting the immense weight of the star, it starts to collapse on itself. The core gets more and more dense as the collapse continues before it reaches a physical barrier, the neutron degeneracy pressure. This occurs when the entire core has been compressed into a blob of neutrons that are packed together as close as physically possible. This pressure preventing the neutrons from moving any closer is extraordinarily strong, and the infalling material hits it like a brick wall and rebounds, causing a massive shock wave. This process, known as a supernova, releases immense amounts of energy, both in the kinetic energy of expanding material and in the short-term brightening of the star. A supernova can briefly outshine the entirety of the stars in a galaxy. When the proverbial dust clears, a neutron star remains, the dense core of the star that caused the rebound. Some stars are so massive that even the neutron degeneracy pressure cannot stop the weight of their collapse. A supernova still occurs, but the remnant neutron star continues to collapse. With no more barriers to stop it, the material falls endlessly inwards. Eventually, the entire mass of the star is contained in an area of zero volume, giving it infinite density. This is how black holes are made. Nothing is known about what happens near this singularity, but the gravity around black holes is so strong that even light cannot escape if it gets too close. The death of stars breathes new life into the universe. The first generation of stars was born when elements heavier than hydrogen and helium did not exist. Heavier elements were created in the fusing cores of these stars and distributed throughout the universe by their violent deaths. Supernovae, as well as some other processes like the merger of two neutron stars, are so energetic that they created even heavier elements, up to and including uranium. This led to the enrichment of the universe and allowed for complex chemistry to happen on the surface of planets. We are ourselves products of this enrichment, as the elements necessary for life were all made in the cores of long-dead stars. The universe is vast, but each of us is a little slice of its history. To quote the late Carl Sagan, "We are made of star stuff."